welcome everyone, also from my side, from our side. We are really excited to be here. Nikki, are you already sharing the slides? Oh, they're coming in right now. Perfect. So, welcome to our presentation about feedback insights, bringing an unsupervised model to production. Let's see. Actually, I already introduced ourselves a little bit, but I might just add my part to it. So hi, I'm Maike Fischer. I'm a software engineer at ING. I've worked at ING for the past 2 years and already mentioned mostly in machine learning projects, building models, but also bringing them to production. Yes, so Nikki, would you like to introduce yourself?
Yeah, hello everyone. My name is Nikki van Ommeren and I'm working as a data scientist at ING. And we're now going to talk about the last project we worked on feedback insights together with Maike. So let's start.
Yeah, let's get started. Let's look at the agenda. So today we want to bring 3 stories to you. And the first one is a bit about our business case. So what was the problem that we were facing with customer feedback at ING? And the second part will be really about the model. So about the machine learning part, what did we try? How did we evaluate our results? Because it's unsupervised. And last but not least, the engineering part of things. So how did we bring this to production? Really well-rounded story. So let's kick it off, I would say. So how do we collect feedback at ING? We collect feedback via all our different channels, mobile, but also web. How you can see here starting at the very left side of the screenshots, we have a sort of small front-end components which ask the customer whether he would like to give feedback about a particular topic. And there's once he interacts with one of the different emojis, another screen opens, and there he can also explain himself, so he can give open text feedback to us. Now, moving on to the next slide. Now, flipping the coin, what do we as ING colleagues see from the inside? And that is the voice. The voice is a feedback application that mostly our business colleagues use, where all the different surveys and all the different responses get collected. So this is a tool that a lot of business colleagues use to understand the customer better. But as you can see on the right side of the slide, marked in red, there is really an overwhelming amount of customer feedback coming in to the voice via all sorts of different surveys that are running across different channels throughout the company in different countries. So our product owner came to us and said, we have so much data, but we have no insight. It takes a lot of time to analyze the open text answers, and we need your help. So here, Nikki and I come into play as machine learning experts, I would say, where we, after a lot of conversations with the users, ended up proposing to build a feedback cloud. And this is something our users really, really liked. So what is a feedback cloud? A feedback cloud is very similar to a word cloud, where the bigger the item, the more text is underneath. So here, let's take the example looking at credit card. There must be a lot of open text, so feedback about credit card in that item. Now, what is the difference between a regular word cloud and the feedback cloud? Is that we provide more context to the text in the word cloud. If you take, for instance, the example inloggen app, that means it's not just talking about app, but there's context around it. So the user now sees in the feedback cloud that there's feedback about logging into the app. So it gives you contextual knowledge about what is going on that you then can further explore and interact with. Now, it's really important to understand that when we proposed this solution, this was a mock-up. This had no model underneath, and we didn't even try a model yet. So we didn't know how to build this, but the users loved it, and they really wanted to have it. So yeah, Nikki, how did we build this?
Yeah, thank you, Maike. So now we were up with the challenge. Okay, we promised to build this beautiful thing. Let's try different approaches and actually build this model. So now we'll explain more about this journey. So to create clusters of similar feedback, as shown in the previous step, we first start with pre-processing. So when a feedback response comes in, we first remove stop words of the English, French, and Dutch language, as our model needs to work for different languages. Within ING, we get customer feedback in different languages, and these are the ones supported at the moment. And we also remove punctuation. The next step is to create a numerical representation, also called an embedding from our text data. To create these embeddings, we explored several options. This was one of the most, I would say, challenging steps in creating our model. So in the next slides, I will explain how we created the embeddings and how we evaluated them before explaining the rest of the pipeline. Okay, so yeah, which models did we try? So now I will explain a bit about the different algorithms we tried. Unfortunately, due to the time constraints, I cannot go into all the details, but I will give you a high over explanation. So the first model we tried is one of the most popular models for creation of numerical representation from text data. It's two-layer neural networks, and vectors that are more similar to each other are closer in the vector space. So for example, king and queen should be closer to each other than king and woman. And to create a representation of the entire feedback response, we calculate the word vectors for each of the words in the feedback and then take the average of the different word vectors. Then the second model we tried is Doc2Vec. And as the name suggests, this model depends heavily on the previous model. But instead of creating word vectors for each word separately and taking the average afterwards, we create one representation for the entire feedback response. And this is done by the introduction of a document ID from which we try to predict the words. And we trained our own Word2Vec and Doc2Vec models on our own feedback data. Then the third model we tried was a BERT model. This stands for bidirectional encoder representations from transformer. And it's a model created by Google. It reaches state-of-the-art performance for many NLP tasks like question answering. And we had very high hopes for this model. So I think at some point we were joking, okay, how cool would it be if we would have a BERT model in production? So I can say this was our personal favorite. And lastly, we also tried TF-IDF. We consider it good practice to also include a simpler model to be able to compare. And what this does, it basically counts all words and then applies a method called TF-IDF, which gives a lower weight to words that occur more often in the feedback. So these are words like you, me, I, and which makes them less important. Well, then let's find out which model gave us the best results. But first I will explain, so we have an unsupervised model, so it's not that straightforward to evaluate the quality of the model. So what did we do? We used a framework based on a framework created by Facebook, which is called CentEval. And this framework evaluates embeddings on different downstream tasks. We created tasks specific for our dataset and trained a classifier for each of the tasks with the embedding from each of the models as input. So the first task is the predict question task. It includes data with answers from 2 questions. So how could ING improve its service? And you're positive about the contact with ING because, and then we created embeddings from the answer to these questions, and we trained a model that should predict this response is giving an answer to question 1 or to question 2. Then the second task is the semantic match task. We create embeddings for 2 feedback response and predict whether they have the same meaning or not. So for example, cannot find my yearly overview and cannot request a scanner have a different meaning. So we should predict a 0, and great app and a nice mobile application mean almost the same thing. So it should predict a 1. Then in the last task, we predict the topic of a survey. So we ask feedback after a customer completes different processes. So this can be, for example, after a customer applies for a mortgage, specific for business customers, or just generic survey when you're using the app. And we create embeddings for feedback in these 3 surveys, and then the model needs to predict, okay, to which topic are they related? And then this is very important. Our assumption is that if a model receives the highest score on the downstream task, it generates the best embeddings. So what this basically means is that we believe that good embeddings contain a lot of information, and then it should mean that the classifier that uses the embeddings also gets the higher score. And we use the same classifier and process for each of the different embeddings. So now to the results. Yeah, so over here you can see the accuracy of each of the tasks for each of the models on the training and test set. So you can see that BERT scores best on the predict question task. The TF-IDF actually did the best in our case for the semantic match and the predict survey. So in the end, we chose to use TF-IDF for our embeddings. We were a little bit sad because we were really hoping for the BERT model. But in the end, it was simple, easy to explain. And this point I wanted to highlight because it's also very important. When we showed users the results of TF-IDF and the model would make a mistake, users could understand why. So they didn't mind that much. But if we showed the BERT results, and sometimes it was really amazing what the results BERT could achieve, but sometimes it clustered weird things together, and we noticed that users were so over-focusing on errors and being confused that we did not feel comfortable to put that in production. Well, the good thing about the process we have now is that it's easy to expand to new languages, but the downside is that it's not based on meaning. So after TF-IDF, we're left with a 10,000 by 1 factor for each feedback response, as our vocabulary is at 10,000. Then in the next step, we reduce the dimensions. This is to speed up the clustering afterwards and reduce it to 300 times 1. We use the truncated SVD for this. Then we cluster the vectors using hierarchical clustering. Then it's interesting to note that not every feedback quote needs to be part of a bigger cluster. Because in our data, some customers are just talking about really specific problems they're having, and they're just not comparable to other feedback. And then in the last step, we create a representation for each cluster. So these are basically the words you saw in the feedback cloud before. For example, rekeningkosten betalen. And we use some simple business rules for this. So we count the words in a cluster, and the most occurring words will be part of the representation after removing the stop words, of course. And then we do a small model, simple model to make sure plurals are seen as the same word. So account and accounts will not both be part of the representation. Well, Now I did a lot of talking, and it's time for some real action. I would really like to show you the real product, but unfortunately that contains real customer feedback data, and I cannot show it to you. So I'm going to show you a notebook, but it has feedback from the App Store in it, because that is public feed. Yeah, that's public data. So. Yeah. So over here you can see I load App Store data, and it contains 1,072 feedback responses. Then I will run the model. Yeah, and you can see the feedback is clustered. So in this case, most of the feedback about rekening iPad staat, then dark mode app, and notification later push. And I also can create a word cloud from this data. You see the same data. And then the idea is that customer journey expert can click on the word cloud and let me see where my mouse is. See them. There. Can click on it and can see which data is in the cluster. So for example, if I go to dark mode app, I can actually see which feedback is in this cluster. So good app, nice if there would be a dark mode. Dark mode works well, does not have a dark mode. So indeed, I think there are a lot of customers are waiting for this dark mode. Can look into one other one, maybe notifications later push. I think push notification do not work, push notification do not work, fine, but notification do not work. Okay, so I guess this is a good point to mention to people working on this feature. Yeah, so this is the way our colleagues would work with our product. And now let's go back to how we actually brought this into production.
Okay, thanks, Nikki. I see we have not too much time left, so I'm going to keep it brief because I think we want to focus also on questions. So yeah, now that we saw how the model worked in a notebook, we still had to bring it to production. So I'm going to talk you through the whole chain of requests from the user perspective. So let's start on the bottom of the slide where we have the front-end application, the voice. We already talked about the voice. That is the entry point for our product owners, customer journey experts, where they can look into their survey. So once they enter their survey, the front end will send a request to the backend application. That is basically where the logic is happening for the voice, the backend of the voice. And within that application, once it receives the request, will then in that request see what type of data does the user request to see in the word cloud. And it's usually already predefined on the page. Once you enter the survey, there's like a default date, which you can also change later on. So depending on these settings, we'll send a query to the database and we'll get that data in batch. So let's say the user requests a word cloud for the past 2 weeks on a particular survey. We get that data from the database on the left side, and the API will then send an additional request to our model container. So the unsupervised machine learning model is running in a Docker container on our private cloud. And we expose the predictions via an endpoint, so an HTTPS endpoint. And we can query predictions from the model by sending the data in the request. And in the response, we'll get the cluster names in it. Then the backend application, once it receives the response from the model, will push it to the front end in the response of the previous request. And then the front end parses it in a very nice looking word cloud. Yeah, so this is how it works on a very, very high level. Well, we talked a lot about good stories, but also we have some learning, some caveats that we have to take into consideration when bringing an unsupervised model to production. So basically, because in nature it's unsupervised, we are training a model on request every time in production. What does that mean? It has implications on several levels of our system. So let's start with the database where we get the data from. You can imagine that a batch request like this has its limits. So let's just say the limit of our database is 5,000 feedback items, hypothetical. That means that we can maximum retrieve in one request 5,000. Now, there's probably ways around it. Maybe we can do several requests. But at one point, our API has to handle all that data. So there are definitely limits. The same goes to sending the data to the model over HTTPS requests. You can only send so much data via HTTPS because you have to serialize that data, has to be sent and has to be deserialized, and so on and so on. So that protocol in itself has limitations. Now, and the model itself also has limitations because you are training in production, and the more you have to cluster, the longer it will take. So you're risking timeouts because once your front end doesn't receive a response from the back end because it's taking so long, it might time out. You don't set that correctly. And where do you want to set your threshold? So we realized that for most cases, it will be fine for us. But let's say you have a business user that wants to make an analysis of the past 2 years. That's not going to happen. So if he wants to have these kind of predictions and these kind of feedback clouds, he has to reach out to us, and we have to do this in a separate manner. But we cannot offer that through the voice itself. We have limitations there. And also to keep in mind, this was our first MVP. So took us 6 months until we went from idea to production. So we really wanted to first generate business value before we overthink these kind of things and build something that is maybe needed only in 1% of the cases. So this is a bit of the struggles that we also had and the difficult decisions that we had to make. But all in all, I think, yeah, we're really happy with it, and our product owner is really happy with it. So I guess that's always good. And I think we're actually pretty good on time. We have 5 minutes left for questions. We planned on 10, but let's see. Are there any questions?
Yeah, thanks a lot for the presentation, actually. And you guys have so many questions, quite overwhelming. I think within the first 7 minutes of your presentation, you started having questions coming in. Of course, we can't take all of them, but then if you guys have the time to engage on Discord, we'll carry some of those questions over there. One of the questions we have received, and also we have more questions outside of this on Discord. So one of the questions we have received is, why did you choose for a model instead of a simple heuristic to group comments, for example, Levenshtein distancing? And similar-ish to this, so there's a lot on the grouping side as well. So there is, like, for example, I saw another one, like, did you try making smaller groups within your larger groups? And what's your take on this whole side of grouping?
Yeah,
so go ahead. No, you go.
Okay. Yeah, so we did play around with different clustering algorithms and with how large and small the cluster should be. We actually also gave the notebook and gave a little instruction on Python to our business stakeholders so they could play with different, like the distance threshold. So they determined in the end how large the groups should be. And so there was really a collaboration between business stakeholders and us. And for this first MVP, we decided that there should be one threshold for every serve and every request, but this is something we can optimize in the next MVP.
Right, and I think I recognize the person who asked this question. So this is coming from Wendell. Awesome talk and great achievement. He has a question that how are the dimensions used by TF-IDF versus BERT taken into account when evaluating the classifiers using CentEval?
Sorry.
How are the dimensions used by TF-IDF versus BERT taken into account when evaluating classifiers?
So basically,
Nikki, I think we had way more dimensions using BERT, right?
I could imagine.
No, for BERT it were 300 dimensions, if I remember correctly, and for the TF-IDF plus the truncated SVD, it is also 300 by 1. So I think we made sure that the dimensions were the same, and we run a small hyper parameter tuning for every classifier in CentEval. That's also part of the CentEval framework we used.
Right, and then I'm going to pick up a question from Discord from Vincent. So what he's asking is that there is a mention a few times that you are really hoping that BERT would be the best, but he really would like to ask, isn't it a huge relief that you can use something much simpler?
Very big relief, because, you know, if you think about, we are already struggling with runtime, or that's a concern of ours. You know, the model can take very long to run. If we would have brought BERT to production, that would have just been extremely unrealistic, to be honest. I want to see a use case where they use BERT, because making predictions with BERT can really take quite a while. We noticed that during experimentation. So huge relief. Also explain that to your product owner, you know, like it's always good when you can explain something to your stakeholders, why things happen the way they happen. And TF-IDF is pretty simple to explain, I think.
Awesome. Yeah, I'll let you take one of the questions from Q&A and then we'll close it up there.
This is a nice one, Nikki. Vinay is asking, are these multilingual data sets? And if so, the embeddings created were separately made for each language or combined? I think this is a very interesting one to talk about.
Yeah, so indeed, we have a multilingual data set. We run the same model on each language. So first we make sure from each feedback quote, we remove the English, French, and Dutch stop words. And then we just apply the model, and we don't make any, we don't do anything different for the different languages. So it could be that sometimes English and Dutch ends up in the same cluster if the languages are using similar words. But if the words are different, like rekening and account, then the feedback will end up in different clusters. So it could be a nice addition to, I don't know, first translate the data, but we thought that's nice for MVP too.
Yeah.
Cool.